Assalamualaikum. I am Dr. Muhammad Yasin Naz from the Department of Physics, University of Agriculture, Faisalabad, Pakistan. Today I am going to present some results on plastic waste management through pyrolysis process and the production of some valuable products through this process. Before I start, I would like to thank the organizers for providing us this opportunity to present our work in this prestigious event. So before we start, I have to introduce the work, what is the background of this work, and then the research gap we try to address in this research, the possible research objectives, and then the methodology adopted to complete this work, then the possible results and their discussion, and finally the concluding remarks. So as we know that plastic wastes are counted as non-biodegradable materials and the reason of multiple environmental and health issues. These materials are not only harmful for human but also for the aquatic life and wildlife that mistakenly eat these materials. Plastics are widely used materials all over the world due to their high strength to weight ratio and low cost. However, economic development of the world is also being affected due to high production of plastic waste. The management of waste materials is a growing challenge which adversely impacting the environment. So roughly more than 60 billion tons of plastic waste is produced in last 6 decades, and out of this bulk amount of waste, only 9% was recycled, 60% was dumped into landfills, and remaining was destroyed or burned. As estimated, 12 billion tons of waste plastic will be accumulated in natural environment by 2025. And in future, only 30% is planned to be recycled and still 70% will be disposed of, which is posing serious challenge to the human health and environment and also to the aquatic life. So there are many types of plastic which are being used at industrial level and household, and these includes the high density polyethylene, the low density polyethylene, polyvinyl chloride, and propylene and polystyrene. So out of these materials, high density polyethylene is the most important because it is commonly used at industrial scale. So our focus is at the moment on high density polyethylene. High density polyethylene is the most prevalent solid waste. It has complicated structure, consists of majority of free radicals, and have this space filling property, and also pose a complicated chain structure. So what we do in this research, actually we understand that for a success of any waste management process or the pyrolysis process, we should have good knowledge of the reactions involved in the conversion process. Normally people do the experiments and then they find their reaction rate constants through experiments, which when they try to implement at commercial scale, they fail to produce the same percentage or to gain the same efficiency at the commercial scale. So what we do, we extracted the experimental reaction rate constants involved in the pyrolysis process from the published literature, and then we do mathematical modeling. We applied the statistical models and we predicted new reaction rate constants statistically, and then we use these reaction rate constants predicted statistically in a MATLAB code to using the second order differential equations, and then we predicted the output, means we find out the output products like the gas, oil, light waxes, heavy waxes, etc. And then the most importantly, we conducted the sensitivity analysis of these reaction rate constants towards the products like oil, gas and waxes. And this is the novelty of this work, because sensitivity analysis of individual reaction rate constants have never been conducted in the published literature. So this research will be conducted with the objectives like we want to save the time and cost of empirical rate constants, because people generally conduct the experimental work to extract the reaction rate constants, but in this case we predict the reaction rate constants through statistical models, and we want to depict the ideology concept and then implement this concept at the commercial scale. And also the objective is to verify the ideology concept through sensitivity analysis, and then we analyze the effect of process parameters such as activation energy involved in the reaction, frequency factors involved in the reaction, and then temperature of the reaction, and then reaction rate constants. And then we analyze the sensitivity of individual rate constants towards the products like gas, oil, heavy waxes and low waxes. Here is the methodology adopted to complete this research work. As mentioned earlier, we collected the experimental rate constants from the published literature, and then we predict the reaction rate constants statistically using our software with the slight difference from the experimental rate constants. Then these predicted rate constants were used in the MATLAB to solve the second order differential equations, and then the analysis were conducted to find out the oil, gas, heavy waxes and light waxes through the MATLAB simulation, and then we conducted the sensitivity analysis of the most suitable reaction rate constant to ensure that what we can get if we conduct the pyrolysis experiments at the commercial scale. So here are the multiple linear regression equations we use to find out the statistical rate constants. These statistical rate constants were obtained with a slight difference from the experimental rate constant. And what was the difference from the experimental rate constants? Actually, we keep three type of differences, means 0.02 difference, 0.03 difference, 0.04 difference. So we obtained these three equations, Z1, Z2, Z3, and these equations were used to extract the reaction rate constant. So when we keep the difference of 0.02, we obtain x1 and x2 values of the reaction rate constants, and these reaction rate constants with the t value and p value are shown in the table 1, and these values indicate that the predicted rate constants are valid for the simulation of the work. Similarly, table 2 shows the statistical prediction of rate constants with the difference of 0.03 from the experimental rate constants, and table 3 shows the predicted rate constants with the difference of 0.04 from the experimental rate constant. These x1, y1, x2, y2 and x3, y3 values were used to find out the complete set of 9 reaction rate constants, and this table 4 summarizes the whole methodology. The leftmost column shows the experimental rate constants which were extracted from the literature, and the second column shows that the statistically predicted rate constants with the difference of 0.02 from the experimental rate constant, and then the predicted rate constants with 0.03 difference from the experimental values, and finally the rightmost column shows the predicted rate constants with the difference 0.04 from the experimental rate constant. So these set of 9 rate constants were used in the MATLAB to find out the products like oil, gas and waxes. Here is the model pathway which shows that which rate constant affect what kind of the output. Like we can see that the K8 is almost affecting the all products like heavy waxes, gas, oil, and low waxes, while K1 mostly affect the low wax, K2 affect the oil, K3 affect the gas, K4 affect the heavy waxes, while K9 affect the oil and heavy waxes. Actually, it shows how heavy wax convert into the oil, and the K6 shows how the low wax convert into the gas, and K5 rate constant shows how low wax converts into the oil. So how these individual rate constants affect the product, this is called the sensitivity analysis, and it have never been conducted in the published literature. So we solved the second order differential equations in the MATLAB to find out the sensitivity of these rate constants to the product, and these four equations from 4 to 8 were solved in the MATLAB, and we find the following results. First of all, we conducted the simulation of experimental rate constant extracted from the published literature. As we can see that the oil yield increases over time, and after 2 minutes and after 3 minutes and 20 seconds, the production of the oil reaches a steady state, and about roughly after 3 minutes we are able to get 73.99% oil and 24.15% gas, and light and heavy waxes initially increases and then they decreases over time. It means that these waxes are converting into the oil and gas. So when we conducted the simulation of the predicted rate constants, initially we conducted the analysis with the statistical predicted rate constants having a difference of 0.02 from the experimental rate constants. We can see that we get almost the similar trend as we obtained with the experimental rate constants. We obtain 73.9% oil after 3 minutes and 24.17% gas after the same time. And similar trend was also observed with the waxes. Heavy and light waxes initially increases and then they decreases over time. It means they are converting into the oil and gas. And these results, if we go to the previous slides, exactly matches. It means that with the difference of 0.02, the statistical rate constants which we predicted using the R software give almost similar results as we can get from the experimental rate constants. However, when we conducted the simulation results with the 0.03 difference, we can see that the oil yield increased to 78.44% and the gas yield slightly decreased to from 24% to 20.72%. It shows that in this case the oil production is higher as compared to the gas, while the light and heavy waxes shows almost similar trend as we observed in the previous cases. When we conducted the simulations with 0.04 difference, and we can see that the oil yield was low as compared to the 0.03 difference, and the gas yield was slightly higher as compared to 0.03 difference. It means that if we want to get the more gas, we have to recommend the statistical rate constants with the difference of 0.04 from the experimental reaction rate constants. And if we want to produce more oil, so we have to recommend the statistical rate constants having 0.03 difference from the experimental rate constant. So at the end we conducted the sensitivity analysis and we find that the Ka rate constant is the most important among all the rate constants because it heavily affects the oil yield. Our primary focus was on the production of the oil, so it heavily affects the oil yield. So we see that the sensitivity of the Ka to the oil is that at the end of the reaction we obtain 79.18% oil which is much higher as compared to the all other rate constants. So these analysis confirm that we have to consider the rate K8 rate constant if we want to produce the high oil yield, and the statistical rate constant having 0.03 difference from the experimental rate constants. So these findings can be concluded as statistical rate constants dominated the experimental work, because having the difference of 0.03 from the experimental rate constants, the predicted rate constants produce the highest oil yield of 78%, and produce slightly lower gas yield from the experimental rate constants. And then predicted rate constant with 0.03 difference was recommended for the commercial scale production of the oil from the pyrolysis of the high density plastic. And then we try to find out the sensitivity of the rate constants, and we find that the K8 means the second last rate constant most effectively affect the production of the oil, and it was possible to obtain the oil from this rate constant up to 79 points something. So it shows that these analyses can be implemented for commercial scale production, but bear in mind that these results, these analyses have some limitations. For example, we conducted these analyses on just one type of the plastic, I mean the high density polyethylene, and when we talk about the plastic waste, there are mixed type of the plastics, high density, low density, polyethylene, polystyrene. So if we want to effectively implement these analyses for commercial scale production of the oil from the pyrolysis of the plastic, we have to reconsider the analysis for mixed plastics, which is our future undertaking. So in future we will focus on the analysis of the mixed plastic waste for the production of the valuable products. So thank you very much.